In this video, we will talk about energies involved in a simple harmonic motion. Let's use a spring system as an example. So here is the setup. We have a spring connected to a mass M, and it's oscillating on a smooth surface around an equilibrium position. So let me suppose that here is the equilibrium position. Let's use this one as the origin of our coordinate system. It's called O, and that's the positive x direction. It's positive x direction, and once the object starts oscillating, it can reach as far as this position, and that's this displacement. The opposite is the positive a. A is the amplitude. You can also go to the left side, this position, and that displacement is negative a. Okay, again, a is the amplitude. Okay, so now think about what energies are involved in this simple harmonic motion. So for the object with velocity v, let's say during the motion, let's say the object is at this location and it has velocity v. Now it's going to have kinetic energy k, which is defined as 1/2 mv squared. Okay, now this position, let's say its displacement is x, let's add position x away from the equilibrium position. Then it's going to have a potential energy for the spring system. So spring is stretched by an amount x. Then it's going to have 1/2 kx squared. That's the potential energy of the spring. That's kinetic energy of the mass. Now, if I consider the whole system, it has both mass and spring. Now, the total energy here is going to be, we call it E, means mechanical energy for the whole system. It's going to be K, that result from the mass velocity V plus U, that results from the spring's potential energy. So that's the total energy of our system. And since the spring force is a conservative force, if you don't know what conservative force is, then you can go back to the chapter where we define the potential energy to look at its definition. Okay, so F spring, the spring force is conservative force. And from its name, we can already guess that it conserves something, and that is the mechanical energy. The total mechanical energy is conserved. So you can say this quantity E here equals a constant, meaning that it's conserved. And it's a constant throughout the whole process, whether the object is at, the mass is at the origin, or the largest displacement at this position, or in between. This quantity is always fixed, right? So it's a constant. So now let's first think about the question, what is this E here? Can we actually do a calculation to find out E's expression? So the answer is yes. Let's use some special position. Let's say I want to use the largest displacement to the right side. So when x equals plus a, the displacement is positive amplitude, then the velocity becomes 0. The velocity is minimum in magnitude at this position. The object is going to stop here at this instant, and then after that it's going to return, moving back. It's going to move back toward the equilibrium position. And at this location, because the displacement is the maximum, so the potential energy here is also maximum. So we can say K is minimum at this location, which is actually 0. And U is actually maximum, which is 1/2 Ka squared. Now remember that the mechanical energy E is conserved in the whole process. So that E is actually this maximum potential energy. This value equals E. So we figure out that it's actually given by 1/2 Ka squared. So it's very convenient to actually calculate this number here. Now let's look at the second special position when x equals 0. When the object, this mass m, is at equilibrium position, okay, at this location. Now, since x equals 0, then potential energy becomes 0. So you can say U here is the minimum, which is just a 0. Now, how about the K here? The velocity is actually maximum, becomes a maximum value. And if you remember the discussion previously for simple harmonic motion with spring constant K, then its angular velocity is square root K over m. And the maximum velocity is omega times a. Omega is this quantity here, square root K over m. So there is square root of K over m and times a. A again is the amplitude. So now we can calculate its maximum kinetic energy, which is 1/2 m V max. V max is omega square a square. Okay, V max square is omega square a square. So the total kinetic energy also equals 1/2 m omega square a square. Okay, so that's the maximum, some extreme positions of either maximum potential energy or maximum kinetic energy of the system. Okay, now let's look at in between, let's say at this position x. Now suppose I tell you that one example calculation here. Suppose I tell you that this x is half a. Now can we calculate what is the velocity at this location? Okay, now for this question we can apply this energy conservation concept. Since I know the total energy is given by 1/2 Ka squared, and that should be equal to the kinetic energy 1/2 mv squared at this location plus the potential energy at this location 1/2 Ka over 2 squared at this location. So let's see what we can get for the velocity v. So here is 1/4 times 1/2 Ka squared. Actually we can get rid of this 1/2 for all terms. And so we get 1/4 here. And if I move this 1/4 to the left side, I get 3/4 Ka squared equals mv squared. So the velocity squared equals 3 Ka squared over 4m. So velocity equals the speed, the magnitude of velocity is given by 3K over 4m of the square root times a. Okay, equals this value. Okay, so here is just one example calculation to show you the convenience of applying mechanical energy conservation to calculate the velocity at a certain position that you already know. So one thing we realize from this calculation is that once you know the position of an object of this mass m, then it's very easy to do calculation for the potential energy, which is 1/2 k times this position squared. And then from there, we can easily do a subtraction of the energy to get to the kinetic energy of the system. Okay, so to summarize this discussion, let's draw a picture. And the vertical axis here are energies, either kinetic energy, potential energy, or the total energy, total mechanical energy E in this y-axis. Now in the x-axis, we have position. That's this position x here. Now at the origin here, we know the potential energy becomes 0, right? But away from it is 1/2 kx squared. So let's say I draw this parabolic curve to represent this 1/2 kx squared. That's this curve here. Okay, and the boundary here, it can go up to positive a and go down to negative a. That's the boundary of this object's motion. And we also call these 2 points turning point. Okay, so that's turning point, meaning that if the object moves toward this turning point, it's going to change its direction and move in the opposite direction. Okay, it's going to turn, make a U-turn here. Now, for drawing the total energy, I'm going to use this red curve, and it's going to be a constant, and its constant value is 1/2 ka squared. So that's why it's going to intercept this 1/2 kx squared curve right at these 2 boundaries. Intercept at these 2 boundaries. Okay. Now the difference between this total energy and the potential energy U here is the kinetic energy. So if I pick a certain location, let's say here, then this length, this difference between E and U is K. This length is K. Okay, so that's so-called the energy diagram. Okay, all right. So that's all for this video. Thank you for watching.